Hello viewers, myself is Dr. Vadiraj Tango, Assistant Professor, Physical Odontology Government Medical College, Mumbai. In this video is Series 3 of Maxwell's thermodynamical equations. This is program for BSc Physics subject, second semester CVCS syllabus. And learning objectives of this session is to know the concept of Maxwell's equations, to understand the meaning of all terms involved in the Maxwell's equations, usage of laws of thermodynamics, and outcomes from this session is knowledge of Maxwell's thermodynamical equations, understanding of each terms in the equations, usage of laws of thermodynamics. Prerequisites for this discussion is concept about first law of thermodynamics, concept about second law of thermodynamics, partial differentiation. In this, the syllabus prescribed for this whole chapter is Maxwell's thermodynamic relations with the derivations, applications of Maxwell's thermodynamic relations to derive Clausius Clayperiyon latent heat equation and Joule-Thomson expansion. In this video, we are deriving two more Maxwell's thermodynamic relations, and we will derive the applications from the Maxwell's thermodynamic relation. One of them is Clausius Clayperiyon latent heat equation. So we will derive Maxwell's fourth and fifth and sixth equation as taking S and P as independent variables, that is x is equal to S, y is equal to P, then differentiate S with respect to S and S with respect to Y. So therefore dou S upon dou X is 1, dou S upon dou Y is 0. Now we should differentiate P with respect to X and Y. With respect to X is 0, with respect to Y is 1. Dou P upon dou X is 0, dou P upon dou Y is 1. Substituting these values in generalized thermodynamical equation, we get this is generalized thermodynamical equation. If we substitute one by one, so dou S upon dou X is 1, then the first term dou S upon dou X keeping Y as constant is 1, therefore remaining term is dou P upon dou Y keeping X as constant term is remains. So it's clear, dou P upon dou Y with respect to X is remains. In the next LHS second term is dou P upon dou Y is there 1, therefore dou V upon dou X is remains. This minus term, therefore equating to the RHS. Coming to the RHS term, dou T upon dou X, noted, dou S upon dou Y is 0, 0 into dou T upon dou X is 0, minus dou P upon dou X is 0, that is 0 into dou V upon dou Y is 0, therefore no RHS terms, only LHS terms here. So replace X and Y as X as S, Y as P, equation becomes like this. But S is, though S is given by second law of thermodynamics as ds is equal to dh upon t, substituting with dou T upon dou P, keeping S as constant, is equal to T into dou V upon dou H and P. This is fourth Maxwell's thermodynamical. Next, coming to fifth. Taking P and B as independent variables, X is P and Y is P. Differentiate the P with respect to X and with respect to Y. If you differentiate with respect to X, it becomes 1. With respect to Y, it is 0. Dou P upon dou X is 1. Dou P upon dou Y is 0. Second, Y is equal to V. Again, differentiate with respect to X and with respect to Y. Dou V upon dou X is 0, dou v upon dou y is 1. Substituting in generalized thermodynamical equation, we get dou p upon dou x, we get like this. With the first term, dou p upon dou y keeping x as constant, into dou s upon dou x keeping y as constant, no terms in the values, minus dou p upon dou y is 0, therefore 0 into the second term, 0 into dou v upon dou x is 0, therefore no term, only one term, LHS term, go to the RHS. Dou p upon dou x, keeping x as constant, y as a constant, into dou s upon dou y, is x is constant, minus dou p upon dou x is 1, and dou v upon dou y is 1, therefore minus 1. And substituting x and y values, x as p, y as v, we got this equation. This is fifth Maxwell's thermodynamical relation. Now we will derive sixth Maxwell's thermodynamical equation, taking p and s as independent variables. Therefore, x is equal to p, y is s. Therefore, dou p upon dou x is 1, dou p upon dou y is 0. Next, it is dou s upon dou x is 0, dou s upon dou y is 1. Substituting generalized thermodynamical equation, first term is dou p upon dou y is 0, 0 into next term is becomes 0, minus dou p upon dou y, no term, dou v upon dou x, no term, therefore keeping as it is here. Dou p upon dou y keeping x as constant, dou v upon dou x, y as constant is equal to, in the right side, first term, dou p upon dou x is 1, dou s upon dou y is 1, therefore 1 into 1 is 1, minus, keep the next term as it is, dou p upon dou x keeping y as constant, dou v upon dou y, x as constant. Now substitute wherever there is x by t and y by s. Equation becomes like this. This is sixth Maxwell's thermodynamical equation. And revision here, how to write the thermodynamical equations. So we know Maxwell's equations are given by here, generalized equation. And here, how to write this is like this. How to write is, so we are P, we are writing the parameters are P, temperature, volume, S, entropy, pressure. See the arrow mark. From T it goes to V and it goes to P. From S it goes to V and it goes to P. So we can write first term, first P and V. So P and V, there are constants, therefore LHS is T, RHS is V. And wherever there is a T, we can make it as partial differential with a denominator as V, it is dou V. And whenever there is a V with a partial differential with a temperature dou T. And we can write this equation as dou S upon dou Y with keeping x as constant is equal to dou P upon dou x keeping y as a constant. And replace dou S by dou H upon T, therefore dou H upon dou V keeping T as constant is equal to T into dou P upon dou T keeping y is constant. So T and V is over. Next goes to LHS of the figure, TP. So TP, whenever we are writing the TP, denominator becomes, wherever there is a P is a constant, we can write it as dou P. Wherever there is a T is constant, we can write as T. And dou V upon dou T at T is equal to minus dou S upon dou P at T. And since we can replace second of thermodynamics dou S as dou H by T, we can write dou H upon dou P at T is equal to minus T into dou P upon dou T at T. Similarly, the denominator of the figure SV and SP are the constants. We can write the same. And further, So TV is over, TP is over, SV is over, SP is over. Next, take the constants as middle, PV and PS. PV and PS, we are writing this. So therefore, we can remember like this, PV special. And from this figure, we can write the constants as PV, PP, SV, SP, PV, PS. In this way, we can write the 6 generalized thermodynamical equations. We will go for applications of Maxwell's thermodynamical relations. Derive Clausius Clayperiyon latent heat equation. So equation is dP upon dt is equal to L upon T into V2 minus V1. We know generalized Maxwell's equation as this. Taking T and V as independent variable, x is T, y is P, dou T upon dou x is 1, dou T upon dou y is 0, dou V upon dou x is 0, dou V upon dou y is 1. Substituting in a generalized equation, we get this equation. Replace x and y's, ds is equal to dou h upon dou t. Substitute above, therefore equation becomes dou h upon dou v, like t is equal to t into dou v upon dou t. Now the question is, in this equation, dou h upon dou v, so dou h is change in heat. If this change in heat is latent heat and change in volume is V2 minus V1. If we substitute in the equation, we get dou h upon dou v at t is equal to t into dou p upon dou t equation. We got L V2 upon V2 minus V1 at t constant is equal to t into dou p upon dou t at v is a constant. So dP upon dt is equal to L into V2 minus V1. This is called Clausius Clayperiyon latent heat equation. Thank you, one and all.